topic of today's conversation is geyser valves, and what we're looking at then is, first of all, before we decide what the geyser valves do, is just to understand what pressure is. We'll have a look at the Cobra pressure control valve ranges that are available and then how they work, as well as vacuum breakers, temperature and pressure safety valves, and then we'll have a look at some bad installations and the possible explosions or actual explosions that have happened due to these bad installations. So then, what is pressure? Pressure can be equated to the force or the weight of an item that works in on a area. So if we take the weight of water in a certain pipe or dam or container and we put that over the area that it is working in on the bottom and we calculate that, it will give us the pressure in kilopascal. But as a rule of thumb, for every 1 meter head of water, and that is that column of water, 1 meter column of water, you get 10 kilopascals of water head pressure. So 10 meters of head will give you 100 kilopascal pressure. If we take, there's a dam on the top of a mountain and we measure from the top of the water level down to where we are measuring the water pressure, say that distance is 8 meters, then we will be having 80 kPa. Easy to calculate, the 8 times the 10 kPa from the meter of head, and then you will get your 80 kPa pressure there. The first valve that we will be looking at is the kwikflo closy valve. The closy is the 100 kPa version and the kwikflo is the 400 kPa version. This is the oldest one in the ranges that Cobra have, and it is fairly complex, but we'll discuss that in more detail a bit later on. The next one is the MASTERFLO 1 valve, and we can see that is available according to the installation information. There is 400 kPa, but it's also available in a 600 kPa valve there. Next one is your MASTERFLO 2, and that is available in 100, 200, 300 and 400 kPa pressure rating. The one that we have now in a kit form or installation form is your master box and your master meter box. So the top one is your master box, PA5-1, and the bottom one has got a water meter in with it, and that is your master meter box, and that is PA5-1M, only available in 400 kPa version. We can see this is a very nice way of installing it because everything can be built into the wall, and then you have your inspection lid which closes it and can be overpainted the same color as your home, and it is not an eyesore or anything like that at all. If we have a look at your SANS 10254 of 2017 edition 4.1, it tells us that we are not allowed to have more than 600 kPa pressure in our system. So no matter what the pressure is that comes from the municipality, we have to have a pressure control valve or pressure reducing valve in the system to make sure that the system pressure cannot exceed 600 kPa pressure. If you have a look at the picture there, it also indicates to us that the pressure rating on the geyser and the safety valve must be the same pressure, because that is what the geyser was tested with at the SABS, Then we also have to have that pressure control valve with it of a similar pressure rating. It has to be either the same or less than what the geyser is. But note that the TP valve and the drain valve are integral parts of that geyser as it's manufactured, so we are not allowed to drop the pressure on the safety valve. So whatever pressure rating is on the geyser, that is what your safety valve has to be. Each one of your different pressure ratings has got a different color, just to make it easier for us to identify them at a distance. If we can't read very well, whatever, we can know exactly what that pressure rating is. 100 kPa is blue, 200 kPa black, 300 kPa brown, 400 kPa is red, and then the last one, 600 kPa, is green. You'll notice on the table that's in front of you, there's two lots of pressure ratings next to each valve pressure. 100 kPa will only give you between 70 and 85 kPa system pressure, so it'll shut off the system pressure when it gets to approximately 70 to 85 kPa. The reason why it's rated as 100 kPa because it is going to start relieving water pressure between 95 and 100 kPa. So therefore your system pressure can never exceed 100 kPa because the valve will start relieving any pressure build up after 100 kPa. Now it's almost impossible to remember all these different pressures, but all you have to do is remember the 100 kPa one because that is a percentage. If you notice, for instance, on a 300 kPa, 70% of 300 kPa is 210. So if we can just remember the 100 kPa one, we can calculate any of the other pressures then. So how do they work? If you notice on the left hand side, the valve is in the open position, so any of your pressure control valves when you receive it is always in the open position. If you blow into it, you can blow straight through it, there will be no resistance because it is open. So the water will flow through there, and then eventually it will start building up underneath the diaphragm, there where your arrow is. As your pressure builds up in the system, more pressure will be pushed in underneath the diaphragm. It'll compress the spring, and eventually the piston won't be able to follow, and as you can see on the right hand side, the diaphragm is actually lifted off the end of that little piston, and water can start dripping then out of the expansion port of the valve. At the same time, the reason why it cannot go any higher is because your main seat at the bottom is closed, and it restricts this piston then from following up after the diaphragm. Now, how much water should a geyser drip? Because we've just mentioned that when it gets to 100 kPa, it's going to start relieving, so it's going to drip. There's a very easy formula: H minus C times liters times 0.0004. H being how hot you are going to be making the geyser or increasing the water temperature in the system. C is what temperature it came in at, so it's basically your delta T. Any change in temperature for the positive times the amount of liters of water that you are heating up times 0.0004, which is the expansion coefficient for water. So in this example that we're showing here, we're heating the geyser up to a typical 65 degrees Celsius. The water, because it's winter now, came in at about 10 degrees Celsius, and we are only heating 100 liters. Remember, it's not the size of the geyser, but actual how many liters of water you are heating up. So in this case, it's 100 times my expansion coefficient, and that will give me 2.2 liters of expansion. Now, this isn't a waste of water. The water has actually swollen and become more due to the heating up of it. Yes, we can waste that water by just letting it go down the drain, or we can run the outlet of the expansion valve into the garden or over the dog's water bowl or anything like that, and we can actually make use of that water that is dripping out there. So that is then your closy valve. You can see it's got the blue label, so it is 100 kPa. Your closy valve is one of your more complex valves. The difference between your 100 and 400 is just in the spring. You can see the right hand side spring is a lighter spring. It has got thinner coils, so that will be your low pressure valve. And then your right hand side one, left hand side one is heavier coils, is a 400 kPa valve there. So inside, if you're not sure what the label on the outside should have been, may have been lost. If you've got a light spring, it's a 100 kPa valve, a heavy spring, a 400 kPa valve. Inside that little cup that pushes up against the diaphragm also, if it's got a big cup, then it is the low pressure closy valve. The smaller cup is your kwikflo valve. So even though it is your most reliable of all the valves, it is a fairly complex valve. You need a lot of different tools and hands and know-how to work on this, and you need quite a bit of skill to be able to service this valve or to work on it. So why do we still keep it? It's due to historic momentum. A lot of installations still have these valves installed, and even some of your older plumbers, that is what they know and that is what they like to work with, so we still have them available as there is a demand for them. The next one then is your MASTERFLO 1. It is a very nice valve in as much as it's got the cap and linings, so you can actually split the valve from the pipe system for replacement purposes, and it makes it much easier, and it's also a much easier valve to work on. You only have the cartridge that you need to replace on the top of that valve where the expansion pipe comes out. That can be split there, and there is a diaphragm, but it's very seldom that you will ever have a faulty diaphragm. 90% of the time, or 99% of the time, it will be your little cartridge there that you need to replace. So there is a picture of your diaphragm then that you're not going to use much, and then the bottom one is once again your cartridge, C-PA 3.862. The newest one of all of them is your MASTERFLO 2. Very easy to maintain. The black section over there, plastic section, can just unscrew by hand, and you can just pop the next one in, and it is very easy. You don't even need any specialized tools to do anything there. So all you need to do is just undo it. You can see how that one is screwing out there, and you can just pop the next one in. It is also very easy to change the pressure rating of the system. For instance, if you're currently having a 300 kPa system and you've put a new geyser in with a 400 kPa and you want to up the system pressure, all you need to do is remove the 300 kPa cartridge, and the 400 kPa cartridge will fit exactly into there, and your whole system is updated to the higher pressure now. So there you can see they're available in the 100, 200, 300 and 400 kPa pressure rating. On the expansion side, also a toolless joint. You just need to tighten that by hand, and where the pipe goes in is a little rubber ball with a hole through it, and that makes for easy adjustment. So you have got approximately 14 degrees swivel in the pipe to each side, so if your pipes aren't lined up 100%, it's not going to put strain on the plastic valve. You still have all that adjustment on the pipe system there. Each one of your valves is fitted with a strainer, but it is always good to have an inline strainer. In actual fact, SANS 10252 Part 1 tells us that you have to have a strainer on your system, because that is what your valve looks like, the top left hand picture, when a lot of dirt has come through the system and been blocked up on the cartridge strainer there. It can make it difficult to get the cartridge out, but it will not get any dirt into your system. The inline strainer just makes that a lot easier because it's easier to open and clean those. The bottom left hand picture, you can see there's actually dirt inside the valve even though your strainer is clean, and this is due to the fact that the person on that installation has had back pressure, so the dirt has actually come from the geyser side or the downstream side of your valve, and no amount of strainer is going to stop that from happening. On another lesson we will go into balance pressure and what that is all about, but that is a typical symptom if you do not have balance pressure. So there it is, SANS 10252 part 1, and it tells us that we have to protect the system from the ingress of dirt to 710 microns. So make sure that all your installations have got an inline strainer fitted. Just the positioning of this valve, it needs to be as close to the geyser as possible. The reason for that is if you start losing pressure through friction and all that type of thing in the system, it's best to have your high mains pressure to as close as your terminal points as possible. But we still need to protect the system from the excessive pressure. In this installation you can see that it is not a balanced pressure installation. Your main supply is coming in and splitting off to the cold water side of the mixer, and only your hot water side is then reduced through the geyser valve, which is an incorrect installation. You need to bring that cold water supply from after the pressure control valve so that both your hot and cold water to the mixing points is reduced to the same amount of pressure. So this is just an extract from SANS 10254 where it tells us that in the case of a 100 kPa system it must preferably not be more than 2 meters below the heater, because that means if it's 2 meters below you're going to be losing 20 kPa pressure already just in that little section without any friction losses and things. So ideally, as we said just now, you want the geyser valve as close to your terminal point and to the water heater as possible. It is also preferable to have it outside because then it is just easier for any maintenance purposes. The next item we're looking at is your vacuum breakers, and they are in there for a very specific purpose. It's not to balance the water pressure, but actually to protect the whole system from any vacuums forming due to backflow or cross fixture contamination, things like that. It will reduce any imbalance of pressure on the negative pressure side, so a vacuum. If we look at SANS 10254, it tells us that it must be fitted to the hot and the cold water side of the geyser installation, and then your hot water side must be on a 300mm riser. If you cannot put it on a 300mm riser, you can take the vacuum breaker 700mm away from the outlet to the water, and then it can be teed directly onto the pipeline. So on the left hand side of the picture you can see the vacuum breaker is in the closed position. If it is in a pressure system, that water will be forcing it closed all the time. As soon as the pressure inside the system drops below ambient pressure, so atmospheric pressure here where we are now, so if the system pressure is lower than what the atmospheric pressure is, the vacuum breaker will open and allow air in to balance the pressure between the inside and the outside of the system. In this picture you can see your anti-siphon loop. The top of the loop must be higher than the geyser, or the top of the geyser, and then your vacuum breaker on the highest point there to prevent any back siphonage happening there. Here we can see if you have your vacuum breaker too low or not at all, it will then siphon out the water from the geyser to the height of that loop. So you can still have hot water in your cold water system. You can burn out the geyser. There's a whole list of items that can happen if you do not have a proper anti-siphon loop fitted to your hot water cylinder installation. We see this geyser broke or imploded because of a vacuum that formed. It's a copper geyser, so it's not as strong as the steel geysers. The wall thicknesses are soft, made of copper, and due to a continuous flexing, due to the pressure and vacuum forming, then this geyser has metal fatigue and will rupture. It will not explode, but it will rupture and you'll have water leaking all over the place. The next items we're looking at is your TP&S, your temperature, pressure and safety valve. We can see on these pictures you can either get it with a male or a female thread. On the right hand side it's got an extra outlet. It's a banjo valve, especially for solar installations or heat pump installations. The TP&S valve works under two conditions, as the name says, for temperature and pressure. So the left hand side one is opening up under pressure. If excessive pressure pushes underneath that diaphragm there, it will compress the spring enough to allow water to come out to drop the system pressure again, so that you do not have an overpressure scenario. This can happen due to the fact that maybe somebody didn't put a pressure control valve in, or the pressure control valve has become faulty or inoperative. So this is a backup system in case of excessive pressure in the system. The right hand side is if it's over temperature. This probe is wax filled. As the temperature in the system rises, the wax starts melting and expanding. It will then push that little piston up until it pushes underneath that diaphragm and forces it open, and thus also expelling some hot water to drop the actual temperature inside the vessel. It is set to open up or to relieve hot water below boiling point, so that you do not have superheated water being expelled to the atmosphere, which can cause an explosion. So then, what does the law say about the pipes and positions and all that type of thing? It says here that the expansion control valve must be on the cold water supply, and it shall be installed downstream of any isolating valve. So you're not allowed to have a stopcock or gate valve or any way of cutting off the water supply between the heat source or the hot water cylinder and your expansion valve. Discharge has 10 different points that we have to keep in mind, and we'll summarize it just now. It says that the discharge of pipes shall be of a size not less than the size of the connection, which is always 22 millimeter. And something that a lot of people miss is the fact that you're not allowed to have it longer than 4 meters. If you need to go further than 4 meters, you need to upsize the whole length of the pipe, and then you can go to 9 meter length. In that length of pipe also, you're not allowed to have more than 3 bends, not elbows, bends, so which is a 45-degree radius. So any bend more than that, you have to subtract 600 millimeter for every extra bend. It must be installed so that the pipe inclines downward continuously so that it can drain. It must be so that it cannot block due to freezing, so there's not allowed to be a trap in that, so where water can stand and freeze up or anything like that. It must be where you can readily observe the flow of water, so it must be outside where it can be seen, but also installed in such a position that you will not risk injuring or damaging people or equipment where the escaping steam or hot water comes out. You are not allowed to join together your TP valve and your expansion valve pipes, and as we said just now, it must be where it is visible outside the building and where it won't cause a nuisance. It also says that your safety valves must be of metal, inclined downwards away from the valve, and it says it shall discharge to the atmosphere where it is readily discernible, but shall not inconvenience the building's occupants or cause damage to the building. So if we want to quickly summarize it, there's your 10 points, Moses and his 10 commandments. It must be of metal, it must slope downwards where there's no trap, the same size as the valve outlet, it's not allowed to be interconnected with the expansion relief, it must discharge outside where it's not a nuisance, where it's visible, where it cannot become blocked, and then you have your limitations, as we said, in the length, no more than 4 meters, or if we have it sized up all the way from the beginning to 28 millimeters, we can go to 9 meters and no more than 3 bends. We're going to quickly have a look at some of the interesting explosions that we've had. I'm not sure how many of you have ever watched the water rocket explosion of Mythbusters, but I'm going to play it for us quickly.
I bet you're wondering why I'm standing here with a plunger.
No, but I'm sure you're going to tell me.
Absolutely right. We have a plumbing myth. Picture an old house, and in that house is an old hot water heater. The hot water heater is neglected. It's beyond neglected. In fact, so badly that it blows up. But it doesn't just blow up. No, this hot water heater blows up like a rocket shooting up through the roof of the house, hundreds of feet into the air, landing 500 feet away. The fans are going nuts about this on the website, and they want us to test it out.
Sounds like fun to me. It gets me all steamed up just thinking about it.
Water heaters are fitted with two main safety devices, a thermostat and emergency cutoff switch to prevent the water from overheating, and a temperature and pressure relief valve to release excessive pressure. To find out what needs to happen to make good water heaters go bad, Jamie and Adam are conducting scale tests using small 6-gallon tanks.
We're going to set this thing up using instrumentation that monitors both temperature and pressure. Then we're going to make each component, each safety component of this water heater fail until we get the entire tank to fail. Anyone have to go to the bathroom?
Improper installation or lack of regular maintenance can really cause the safety devices to fail. Jamie and Adam are just simplifying the process.
This is the thermostat and the emergency cutoff switch, which the water heater normally comes with. We've taken it off, so we've got no emergency shutoff.
The T&P valve is now the only functioning safety device. So here's how it works. When heated inside a closed environment, water expands and causes an increase in pressure. If the temperature or pressure gets too high, the T&P valve opens.
So in theory, once this thing reaches the pressure that the pressure relief or the temperature relief valve activates at, we should just see it start to spew some water.
Yep.
So people don't get scalded, the recommended set temperature for water heaters is well below boiling point of 212 degrees Fahrenheit.
Look at how fast the temperature's rising, man.
Yeah. Won't take long.
When the water gets up to a dangerous 165 degrees, the T&P valve comes to the rescue.
Oh, there it goes.
Really?
Yeah.
Oh, yeah, look, it's spewing. That's what it's supposed to do.
That's better. For their next test, they're really putting themselves in hot water.
What's next?
Well, next, I think we pull the T&P valve and we start the final failure analysis test in which nobody approaches this bunker until we hear boom or all clear. Now, you might wonder exactly how that's going to happen in real life, and I'm going to play it out for you. A homeowner looks at his hot water heater and sees that there's this thing sticking out in a pipe that doesn't go anywhere. And he thinks, well, maybe that's from some old plumbing. It's dripping water too, so I'll just cap it, stop it from dripping water. Happens all the time.
Removing the TMP valve could cause a serious explosion, so Jamie rigs up an external emergency release so they can defuse the system immediately.
Are we live?
We're live.
All right, let's get everyone in the safety zone.
The pressure slowly builds. Normally, a TMP valve is set to release at about 150 psi. Now, the sky's the limit.
This is excruciating.
Tell me about it. 400 psi.
250 degrees Fahrenheit.
Both the temperature and the psi are climbing steadily when all of a sudden,
Whoa. We just lost pressure. We lost half of our pressure there.
something in the system is causing the pressure to drop rapidly.
We're at 300 degrees Fahrenheit. I think we're losing pressure somewhere we can't see, and we've just got to abort.
All right, well, I'll pull the valve. That's what it's for.
All right, let's do it.
Jamie triggers his emergency release. When water that's been heated beyond boiling point hits air, it turns instantly into vapor. Great for opening those pores.
Okay, that is indicating it's fully depressured.
The PSI gauge just failed. Don't know why, but the main thing is neither Jamie or I feel comfortable doing the test here in the bunker anymore. After watching the amount of steam that came out, knowing how much pressure it takes to make a tank blow, we just want to be far away from this.
The pent-up fury inside this tiny tank has got the guys running for cover.
We need more room, for
Let's
sure.
pack up and move it out.
Okay.
Explosion danger lurks in thousands of typical hot water heater installations because the great majority have either improper protection or no protection at all.
Is the tale of the water heater rocket really true, or just over-the-top scare tactics? To find out, Jamie and Adam have arrived at the wide-open spaces of Alameda Naval Base.
It may help you to think about this in terms of just a pure release of energy. All we're doing is putting energy into the water heater in the form of electricity converted to heat. We're not letting that energy out in any way. Now, the difference between a rocket and a bomb releases all of its energy in every direction at once, and a rocket releases all of its energy over a little bit longer period of time in one single direction. And that's what we're looking for here.
The same as their scale tests, they're using a 6-gallon tank. And to recreate real-life circumstances of shoddy installation and neglect, have made a few adjustments.
The electronic cutoff switches and thermostats, gone. The temperature and pressure valve, gone.
The power from a remote generator is switched on.
Okay, Adam, we're live. We're hooked up. We're running about 25 amps. So everybody be on alert. Over.
And our little heater has his moment in the sun.
Well, as far as I can tell, everything's good to go.
I hope we get it to blow this time.
Yep.
I'm tired of watching the heater not do anything.
Third time's the charm.
In a healthy appliance, the cutoff switch would activate before boiling point, and the pressure release valve at 150 psi. But our patient is sick, and his temperature's rising rapidly.
All right, so we're at 7 minutes, almost 40 psi and 250 degrees Fahrenheit.
270 degrees, 53 psi. Okay, we're at 20 minutes, 370 degrees, and 190 psi.
Suddenly, his fever breaks.
That's a failure, but that's not an explosion. It was pretty spectacular. This thing bathed in a cloud of hot, scalding steam and 300, 400 degree water. It's ludicrously dangerous.
6 gallons of water turned into 9,600 gallons of fissuring vapor. But even with all that force, the tank didn't go for a ride.
Let's get a bigger heater out here. Try this again.
Okay, let's do it.
A bigger tank may give the guys the heave-ho they need. can an ordinary, everyday water heater become a rocket so powerful it can blast through a building? So far, Jamie and Adam have let off a lot of steam.
There we go.
Whoa!
But couldn't send a small 6-gallon tank skywards. This time, they're using a 30-gallon tank and have a new strategy to add some extra thrust.
I'd like to fill this 80% full.
Okay.
So let's put 24 gallons in here. We may find this like perfect relationship between water and steam for getting the maximum amount of pressure.
In daily life, a water heater is an appliance nobody normally takes any notice of. So to mimic one in serious neglect, Jamie and Adam disable its safety devices. Once again, it's time for launch and to man bunker boiling over.
By the time we're done with this, we'll actually know what we're doing.
At least one of our crew seems to think they'll get it this time. Never has a single water heater been covered from so many angles. Maybe all this attention will raise them from their D-list apparatus status.
Okay, now we're at 160 psi. It's officially a no-go zone. Anything goes from here on in, so stay clear.
These pressure vessel ones are really difficult because they involve tons and tons of waiting, and it's excruciating. It's really boring. The suspense is killing me.
After an excruciating 50-minute wait, they achieve liftoff.
Wow!
That was at about 350 psi.
That's very interesting, but that isn't a TV show. Does that actually happen in real life? Well, let's have a look at a couple of them. Yeah, in Bloemfontein, this is in Afrikaans, but I'll translate it. It says like a missile. Warm water system went through 2 concrete floors in the Maitland Hotel. This was, yes, superheated water explosion of the heater. This is what it looks like afterwards. There you can see on the right hand side the hole where it's come through the floor. It's gone through the next concrete floor. So it's gone through 2 floors. It hit into the 3rd floor. And there you can see it's lying, dropped back into the 2nd floor's hole. So yes, definitely happens in real life. And this isn't just an isolated case either. Yeah, this was a soft roof. Geyser was up in the roof and it blew all the tiles off. The left hand side one was a fiber geyser and that went off like a missile also, blew out all the windows and the actual cylinder went through the roof. Right hand side one in Honeydew was a copper geyser, so not even a very high pressure geyser, but it's not the pressure in the geyser, it's the superheated water that gets released suddenly, which turns into an explosion. So normal water at ambient pressure boils at 100 degrees Celsius at the sea. Yeah, by us it's a little bit lower because our air pressure is lower here than what it is at sea level. But at 400 kPa, which is your standard geyser that everybody uses, it is 152 degrees Celsius water boils at. So if you have to suddenly open a tap or for any reason drop pressure in that system, that water is going to instantly turn from water or liquid into a gassy steam, giving you that superheated water explosion. So if you have incorrect installations, the dangers there is of scalding, having these explosions. It can contaminate areas and it can damage you and your home. Here are some of the fairly bad installations that we have seen through the years. This one is polycop piping. Now you can imagine if that plastic piping has got heated up to about 150 degrees Celsius, that is so soft it's just going to pull out easily, and then obviously your whole system pressure is going to drop and cause that explosion. This one, I don't know what the guy was thinking of. He's got all the fittings there, but in totally the wrong order and combination of fitting. The left hand side one, the guy must have had water conservation in mind, because we see it goes from the safety valve and gets teed directly into the hot water outlet. So if the safety valve had to open up for any reason, it's just going to put that hot water back into the tank again. You're not going to be relieving it to where the law said, outside where it's visible. Just some more shockingly bad installations. See, this one must have leaked at some stage, and somebody's there put a plug in it to stop it from dripping. Beautiful. I hope you enjoyed this little talk that we had. If you have any more questions or need more information, you're welcome to contact our after sales support department on 0861 21 21 21, and I thank you for your attention.